Welcome, developers. So we need to make a small update because I got feedback from Asobo that actually what I tried to do, I did the wrong way. So I updated the slides, I updated the information, and re-uploaded a video. So this will be a mix of previous things and new things. Mostly it has to do with tagged data, of course, because that was my big gripe. And I found out that it works a little bit different compared to what I thought. So let's go. Welcome, developers. Welcome to this 11th episode on programming with SimConnect. And today we're going to look at ClientData. And I've given that the subtitle when SimObject data isn't enough, because it offers us some interesting possibilities for communicating. Now, let's start, and I'm sorry if that's a bit predictable, with a bit of history again. Some of it I've already touched upon, but we have to start out and discuss how add-on aircraft started out. They generally had a 3D model for the outside view, and then 2D cockpit panels for the so-called 2D cockpit. This is simply the limitation, because 3D was there, but to give a real cockpit where you could interact with it was still out initially in the earlier versions of Flight Simulator. So you would give a 2D cockpit, which was just an outside view of what you would see through the windows of the cockpit, and then put in front of that more or less nice looking panels with gauges. And then there was, especially in the later versions, the option of also providing a 2D cockpit model, or 3D cockpit model, sorry. But actually those 2D cockpit models or panels were quite common up to and including Microsoft Flight Simulator X. Those gauges in the 2D panels were in separate files, and you could make them as a DLL, but most common was to write them using an XML file. That XML file would describe things like put this image here, put that image there, then use this SimObject data to determine whether this image needs to be rotated or moved, or maybe left out. And a lot of the actions in there, including those things deciding how to show it, was done with scripts. Those scripts were in a stack model language, which is something that, especially in the early days of microcomputers, has happened before. There was a language called Forth that was very popular, because stack-based languages are pretty efficient. So you can make a language that allows for quite a lot of functionality, while, even though it's interpreted, is very efficient and good performing. Then those scripts could, of course, read and also write SimObject variables. Now, SimObject variables come in different categories. There was a category K for the keyboard, M for the mouse, but also A for airplane, which were generally the SimObjects, or the SimObject variables associated with the airplane of the user. And there was also the L, or local category, and those were free for those gauges to create and use. Now, the thing is, of course, if you create a variable and put a value in it, and then in another gauge read that value, you've got a way you can communicate between those. So this would allow you to do things in one gauge or with buttons on a gauge that then had an effect on another gauge, even if that effect was not reflected in the SimObject's variables for the aircraft or the environment. Now, communicating using those L-vars had a very big restriction, which was that they were not exposed through SimConnect. So you had to write a gauge, either an XML or a DLL gauge, and that way you could get at the L-vars. Some tools like FSUIPC expose those L-vars, but mostly it is done for add-ons written as part of FSUIPC. There are some ways you could export them again, and actually what you saw with many add-ons that did things like maps or communicate with other computers is that they would have a part that needed to be loaded as a part of the flight simulator process that would be able to read and write L-vars, and that would then expose those values to the outside world. Now, Microsoft Flight Simulator 2024 fortunately no longer has that limitation. Asobo has removed it, which means that now any add-on that can talk through SimConnect can also use those L-vars. Still, there is one big restriction here. You cannot scan for SimVars using SimConnect. So if you don't know the L-var exists, you cannot find out it does. There are some add-ons that do that. And of course, any add-on that wants to allow you to write add-ons that use your aircraft or the special features of your aircraft, they will publish a list of the L-vars of that aircraft. And an example, for example, is the Aerosoft Airbus series for Flight Simulator X and later Prepared, which used to publish those lists. But there is an alternative, and that is ClientData. Now, ClientData actually works mostly like we already saw with SimObject data. You build a define block, and then you request while referring to the define block. But there is one big difference. Now the block is the one that has a name and a fixed size. There are fields, but they don't have names or even units. So if the publisher of a ClientData block returns a value in feet, you cannot say, I want that in meters, or the other way around. Flight Simulator will not be able to convert that for you. So you get what is sent as it is sent. But there are some things here that you can do with it. What is the same is that you can use tagged transfer. And this is the update that works, and it works very nice indeed. Now, the flow for a publisher of ClientData is that you map a name to a local ClientData ID. As usual, this ID is local for you, so anybody else who wants access to that ClientData needs to know the name. They don't need the ID, they map their own. Then you create the ClientData area. You specify the size of the entire block in advance, and you specify if you are the only one that is going to write to it, or if you will allow other add-ons to write to the same ClientData block. And then, just as with SimObject data, you define the block. Now, the big difference here is that there is a very limited set of fields or field types that you can use. Fields are integers or floats. If they're integer, it's an 8-bit, 16-bit, 32-bit, or 64-bit integer. It's always signed. Floats are 32 or 64, so float or double. But there is an escape. You can define a raw field by just saying I want a field of this many bytes. In that case, the flight simulator doesn't know anything about the field, will not try to look at it. Whenever you want to publish data, you set the client data. The defined size must match the block size, unless, of course, you're using tagged fields. Okay, so on the subscriber side, we now have some very interesting things. It starts out the same, actually, by mapping a name to a local client data ID. But when you define the block, again, you use those fields, integers, but you can also use offset and then the size, if you're using raw or one of those numeric types, to selectively map parts of what is published. This means that on the subscriber side, you actually can map for only parts of what is being sent over. This doesn't mean you necessarily don't get it, but if you combine that with tagged requesting, you get only the fields that you're interested in. And this, of course, makes it very powerful. So you can request data, where we can use the same periods as we've seen with SimObject data, with the exception of the simulator frames. It does have the visual frames, but not the simulator frames. But there is an additional, well, call it a period, which is on set. And this means that it will be sent to you every time there is a value pushed, even if it's not changed. Then additionally, you can use the flag for only sent when changed. And this makes Flight Simulator actually compare what you've specified in fields, so which parts of the block you're interested in, with the last one, and use that to decide whether or not something changed and whether or not it will send it to you. Combine that with tags, and you can actually get just 3 fields out of a struct of a few hundred fields and say, I only want those when they're changed. And then you will indeed get very small messages with only those fields and only when those fields have changed. And that's, of course, very nice. But for this, you must specify the datum ID parameter because it is local to you. So do not depend on the datum IDs used on the publishing side. You specify which fields you want and you give them a datum ID, and that is the datum ID used for the actual messages that you receive. Now, I've already noted that when you create the area, you can specify who can write to it. This means you can have bidirectional or multi-directional transfers. When creating the block, you can specify read-only, and read-only means only the creator can set data. However, default means anyone can send. All other clients will receive it, but there's no identification who was the one that made the change or set the data. Personally, I would have said that you change that around and call the default read-only and the multi-writable as the non-default. But, well, this is the way it's been done. A big example here is, of course, the PMDG control area, which is the way you can send events to buttons, knobs, and switches on all your panels in the 737 or 777. And they use a control area, which is 2 values, the event ID and the value to send to the aircraft. And they've made it multi-writable, so you can set and send something to the aircraft, and the aircraft will then set the ID back to 0 when it's ready for the next one. The alternative, of course, is that you use real events or flight simulator events. And in that case, you do not need to wait because those are picked up from the message queue when the PMDG aircraft is ready for the next one. And actually, that's all there is to client data. So given that you've already seen quite a lot of how SimObject works, we can immediately go to the demos that I've made. Now, if you've been watching GitHub, you know that there are now actually 7 demos available. And let's start with the first one, which is simple client data, and it will use the raw SimObject calls. Okay, so I've started Flight Simulator in the background, and I've opened up Visual Studio. If you've been looking at GitHub, you know that actually I do most of my builds by now using CMake and Clang, because I like the way that works and integrates with Visual Studio Code. But this works as well. And there are project and solution files in the GitHub repository for it. Now, most, if not all of the demos actually more or less look like this in their main function. So there's not much happening here. Let's just skip that bit and go up. This is the message handling, and we will first go to the first step, which is to subscribe. This is the receiver. Let's start with the sender here, and let's start here with setup client data. In setup client data, as I said, the first call you make is to map client data name to ID. In this case, the name is here dutchflightsim.hello world, and the client ID is 1. There's not much interesting in there. It's always the same. And then I create client data, and I use a struct. This struct just contains a single array of character of 256 bytes. Very simple. If you want, I can show you. It's in the shared header, and it's like this. There's nothing special going on there. Then, of course, we need to create the define area, and that's the next thing we do. So we add to the client data definition our definition ID. Then you can specify the offset within the define block. Usually you will just use auto and let SimConnect put the fields one after the other. And I just have that single struct. And that's all we need to do to prepare for this. Then on the send side, we have a send message. And what send message does, it puts a message into the message struct and then says set client data, the data ID, the define ID, just default sending, not tagged sending, and the buffer. And when do we do this? Well, we do this in our standard message loop, where we go on until we have a specific number of updates. And what we do is we check if it's time to send the next one. I try to space that out in about a second. And then we send that message using the send message procedure above. So that's pretty simple. All it does is create the client data, define the area, and then while waiting for any messages to come in, every other number of seconds, it will send a message, hello world update with an update number. Simple. On the receiver side, we have the converse. We need to subscribe to this client data. So again, we map the client data name to the ID. Again, this is our local ID. And then we add the struct to the client data definition block. And we request the client data. We request it on set. So every time a set is done on the other side, we immediately receive it. And we use the default flag. We don't need tagging. And then we have the handle message loop, which simply says that we go until we either have a deadline, or if we have no deadline, until the flight simulator stops. And we have our usual message loop with now one big difference. We now check for receive ID client data. And if we have that, then we cast the pointer, we check whether it's our request, and then we send a message received with the contents of the data block that we received. Pretty simple. So let's see what happens if we run this. And we're going to start the sender on this side. And it immediately starts sending. So let's start the receiver here. And you see number 5, number 6, number 7, number 8, 9, 10. And then it stopped because on the other side, it just sent it 10 times. So you see here, you don't get called for old messages. You only get called on set. So the first 4 we miss because that was the time needed to start the other side. There is no queuing, no waiting of those messages. So of course, that is something you would want to solve by having some kind of interaction. So let's go back to the slides. Okay, we're back. This was our first demo, but we can gather some remarks. First of all, you can define fields at specific locations in the block, but usually you don't. You just use client data offset auto. Then most of the time you will request data on set because that's simply the easiest way to do it. Unless, of course, your client is dependent on the timing in those periods. For example, every second or every, I think visual frames are there, but not simulator frames, something like that. But you have to check the documentation which are possible. Okay, this is just simple one-way messaging. So let's have a look at multiple writing clients where we can have the clients play ping pong. Okay, so let's take a look at the source code for this version. It looks pretty much the same. So we immediately start with our setup client data, map client data name to the ID, and then we create the client data. This time we have ping-pong data, a different struct, and I can show you that here. It only has a data size of 8, so it's a message of only 8 characters at most. But the difference now is that rather than using the data flag read only, we use the data flag default. And this means that not just we as ping can send messages, but the other one, pong, can also send messages. The rest is just the same. We define the define block, and now because we're doing two-directional, we request also on the sender side. And you see there is no real problem with doing that. We use the same define ID. We use the same client data ID. That's all fine because it is the same client data area and it has the same structure. Of course, we're requesting it here on set and we're using the default request flag. Then we have not a send message, but rather a send ping, which simply puts the message ping into the client data block and then sets the data. And the handle messages is, of course, now also looking at client data messages because it wants the messages on the other side. And what it does is first it checks, is it our request ID? And if so, did somebody put Pong in there? Because then we need to prepare for sending a message back after a second. And then we send a ping. And if we look on the Pong side, again, much the same as before, map the client data name, add client data definition, and then request client data. Just like before, the only difference with ping is that Pong doesn't create it because that's not our responsibility here. Then the rest actually seems pretty much the same, only now we don't send pings, we send pongs. And in the loop, of course, we check whether we got a ping, because then we wait 1 second and send a pong back. So let's see what that does actually. And let's start the ping side and then wait. And then on this side, and of course, we need to first start the pong and then start the ping. Sorry about that. And now you see that it works. So every time ping gets a message back saying pong, it waits a second and then sends a ping over. And this side then sees that, waits a second and sends a ping back. So it's just a very simple way of showing that you can have multi-client communication using client data. We'll just stop it and go back to the slides. Okay, so back from the demo, and let's add a few remarks. This is a very nice way to exchange data. And Microsoft Flight Simulator is detecting which fields changed. That's not demoed here, but there are demos included that do use that. And of course, using tags makes that even better. And there is a new demo, 11.-8, and that will be at the end. But let's first go and have a look at the C++ version, which uses my library. And I'm going to use the PMDG 737NG for that. There are two standard demos in the PMDG SDK for monitoring MCP data and the CDU screen, and I made updates to that. So let's take a look at that. Okay, so again, the main function is not very interesting. It's the same as it always is. But let's go up and take a look in our test function. We set up a connection and a Windows event handler. And then, of course, we create a so-called client data handler based on our Windows event handler. Then we register a default handler just to make sure that we get a message when there is some message coming in from Flight Simulator that we don't do anything with. And we check for the open, quit, and exception messages. So this will be the same in all later programs, so we can skip that from now on. So when we open the connection to the Flight Simulator, we're going to monitor the MCP displays, which is the control display control panel that you have in front of you as a pilot. We're making use of the PMDG defined data areas, and if you want to do this yourself, make sure to read the PDFs that come with the PMDG SDK, because you need to make sure that a certain file sets the sending of this data to on. Otherwise, you won't receive anything. Now, we're making use of a raw client data definition. This is like the data definition that we've seen for SimObject data, only now it's for client data, and it's called raw in the sense that we have a single record and that is all there is. So it's pretty easy. You don't need to add any fields. You just say, I have a data definition for this record, and that is what I want my client data area to be. And it takes care of the definition for you. Then we keep track of the MCP state, and we request client data, and we give it a lambda. This lambda is going to be called every time data is set, no limits, and it's only when changed true. And we process MCP data, and that is a function that we'll look at next. And then we handle until closed, or of course, Control-C is pressed. So let's go up. And here, what I'm doing is simply looking at the PMDG data and the state we have recorded since last time. And we check whether or not the MCP is powered. If not, we say it's off. If it is, we register that in the state. And then we look at heading values. If it's different than the last time, we print that out and record it. We do that for altitude, we do that for speed, and we do that for vertical speed. So if we go and take a look at the program when it's running, because of course I have started, let me go there. Here I have started Flight Simulator with the PMDG 737. So now I'm going to start the program. And you see it says heading 279, altitude 10,000 feet, speed 100 knots. And that is exactly what we see on the MCP on screen. So if I go here and then turn the knob, you see that on the left side here, the values are received by us. And this also works with that interesting effect where you turn a knob quickly, because then it will take bigger steps. I don't know if you know that. So we're going to go fast. If I go slow, it will go 1 degree every step. If I go fast, it goes by steps of 5 or even more, as you can see here. So this all works. And this is a very simple way. Take a look at the PMDG SDK, because everything that is here on screen, it has a field in there, and you can see everything and you can control everything. So it's a very nice way of getting very detailed information on what is in here in the cockpit, and it also tells you how to change things. So let's go to the other one, which is not about the MCP, but is about the CDUs, because you can get those as well. Okay, here we are in the application for the CDU printing. And as you can see, I've already started it on the left side. And this one is a bit more complex because it renders a screen. And yes, I made use of GitHub Copilot because it claimed to be able to get the terminal window to actually do positional displaying. So it's going to enable NZ the virtual terminal, and then do things like move to row column and print things at several places. And I even had a small bug crop up that I made myself by cleaning up and forgetting that I needed to print everything as a character, but that's working right now. Take a look at the source code if you want, but mostly let's just look at how it works. So here I have the CDU, and it says nav data out of date. So we press clear, and you see on the left here that it actually removes it from screen, and we go to the FMC and do pause in it and say that we're on my favorite airport of Groningen Airport, Echo Hotel Golf Golf, and put that on there. And you see everything works, and it displays this. And what is happening is that the PMDG add-on is publishing this and sending that data to us. So let's go and take a small look at our slides. Okay, so we're back from the 737 and back with the slides. Let's just add that most of the time you will use this raw client data definition. The reason for that simply being that in most cases you will talk with some add-on that simply has one big block of data and wants to send everything. However, you can use other versions, and there are 3 demos for them, which is mapped, custom, and stateless. The mapped client data allows you to say, well, I have this struct and I will generally use everything, but I want to be able to set or receive single fields, in which case you can do that by field mapping. Then there is custom client data for the time when you say, well, I sent this, or at least it is being sent to me as an integer, but I want it read as a Boolean, or the other way around, or you want conversions between floats and integers, simply because you are not the one who wrote the other side of the communication, so you have to adjust. And the stateless is a very interesting one, because there you say, I'm not really interested in the entire struct, so to speak. I'm just interested in providing lambdas for the individual fields or elements within that struct. And there is a demo there with Ping-pong, and that shows that how that works. But because in the meantime, since the last time I made this video, I've had some discussions with Asobo. I learned a lot more about how client data and tagging works. And there is a new demo added to the collection. So let's go and take a look at that one. Okay, so we're now in Visual Studio, and Flight Simulator with the 737 is already up and running in the background. But first, let's take a very brief look at the header file that PMDG has provided. Because here you see it has the names for the different client data areas that it provides. But the most important one is this big struct, PMDG NG3 data. And you see it has lots and lots of fields in there. In the comments, you can find information about the values in those fields and how to interpret them. But you see that there is here flight control, gear, oxygen, engine, fuel. I mean, really everything that's in there in the cockpit that can be controlled, it will be in here. So there is a lot. And if we just want to make something that is interested in the MCP, which is here, the mode control panel, and we just want a few of those values, then we don't really want the rest. So what I did in this particular demo is that I'm going to define a few variables that will contain the value last received. And then I use a stateless client data definition. And I'm going to say, first, I want to add an 8-bit integer. And it's the field called MCP indication powered. So if we would go here and we look for MCP indication powered, it will be let me see. Oh, like this. Here, and you see it's a Boolean, which becomes a single byte field, and I just want that field. So I'm telling the library here that I'm using the offset of this field within that struct. And every time a value is provided for that, then put that value V and just print it out, power on or off. I have a second field, which is a float, and that is the IAS Mach value. So that's the speed, the set speed in knots or Mach on the MCP. And again, I'm saying, well, I want to put that in my last values, record it there, and then print out a value. And it goes on here for the IAS setting, the MCP heading, MCP altitude, vertical speed, whether or not that's blanked, and it provides these lambdas for each of them. And then I request the client data tagged and only when changed. So that means that if I just change, for example, the heading and only the heading, I will get only a tagged field for MCP heading. And only this method or this lambda will be called. So let's run that. And let's go here. So if I go and turn the speed knob upwards, and you see that it says speed has changed, and only that one is printed. So it really is only that field that has been sent to me. The same, of course, for a heading and for altitude, just like before. So this is why I said that I think this is a very powerful way, because if you have something like that PMDG and you have this huge client data block and you're not interested in everything, just in a few fields, you can use this to define those, request those, And Flight Simulator will only call you when specifically those fields have changed, but none of the rest, which is, of course, very nice. Of course, you do have to be respectful with that, because if you do that for all the oodles of fields in this struct, then you do end up with a huge number of requests that are active at the same time, and Flight Simulator will have to compare values between the new one and the old one for every one of those fields. So be respectful, but I mean, not just for the PMDG, for other uses as well, this is a very powerful option. Okay, so we're back from this extra demo, and let's continue. So Microsoft Flight Simulator is detecting which fields change, and if you want to use that and benefit from that, use those tags. Yeah, I was wrong. I admit it. They do work, but they work if you use them on the right side. I was depending on the wrong side to provide those tag numbers. Okay, wrap up. ClientData is great for exchanging data between add-ons. And I mean, that's just it. That's what this whole session was about. Next time, we'll take a look at flow events. Flow events are kind of the new version of the system state events, and they've been added in 2024. So we'll take a look at those. And there's also two calls you can do for setting system state and setting system event state. So let's take a look what those do and finish up the global or system events part of the list of the API. Okay, that's it for this time. As usual, I do this for the subs and likes. So if you like, send me one of those, and I'll see you in the next one.